Hello everyone, welcome to a new video in our Big Data and Platforms class. So in today's lesson, we're going to talk about what is big data and data sufficiency. So one of the quick key questions that everyone is asking, especially when you are learning about big data, is what is the threshold? Like which is the number where you can start thinking about big data? Well, the answer is that there is no a unique number. It's relative. It's relative to your company, your capacities, and it's relative, of course, about the period of time that you are asking. Let me show you this timeline to give you an idea what was considered big data at that moment. So in the 90s is where we have the concept of big data. That's the birth of the concept. So first time it was defined. So typically the data size was megabytes, gigabytes. So 30 years later, that's just, like a personal computer, even a cell phone is going to handle that easily, right? But at that time, that was huge, especially gigabytes, right? You have hundreds of gigabytes. That was difficult to manage at some point. So typically, they had relational databases, SQL, right? Structured data. Now in the 2000s, it's when we have the rise of the internet. So big companies such as Google, so they started having like bigger databases in the order of gigabytes, even a couple of terabytes. So they require solutions such as Hadoop, MapReduce, and NoSQL to be able to store and, of course, to process that data. So it was difficult to handle everything in a single machine, right? So you were required to have a cluster of machines to be able to analyze all that data. Now, the number that I'm giving, that's mainly for big companies, but of course, for smaller companies, the threshold was smaller, right? Okay, in 2010, so that's when we have more like data science, being a data scientist was a huge thing. At that time was considered something big, and right now it is. So with these companies now, the amount of data that was stored and processed was more in the order of terabytes, even petabytes. So they need to create different frameworks. So that's when we have Spark, which is used for to do analytics and machine learning when you have big data, and of course all the cloud platforms. We were also experiencing the Internet of Things. So the amount of data that was created during that time was huge. I'm not just talking about the volume, also about the velocity. Remember the V's. And nowadays, we're right now, I'm talking about 2025. So we're experiencing, of course, we still have big data. Now, big data is not a buzzword. It was a buzzword in the 2000s, but right now it's just part of the, of our reality. So all big companies are facing big data challenges. So now that we use AI, and to be more specific, we use large language models almost on a daily basis. Well, they require big data for the training. I will show you in the next slide the size of the data that was required for the training. And nowadays, we're also we see that these large language models now they are being integrated to be multimodal models. That means that they integrate different data types, not just text, but also they have the capacity to create images, video. But of course, those data sets are bigger, right? Because of the format of the data. So what's next? We don't know, but of course, what I can tell is like the amount of data, not just the volume, but all the other bits are gonna increase, right? The complexity of what we face, and that's what we see nowadays in 2025, where like big tech companies they are kind of like in a race to create data centers, not just with storage capacity, also with processing capacity. They have GPUs, with cooling systems, because they tend to overheat, right? Also, as we speak here, there is also some developments in the quantum computing side, which most likely is going to be the next thing in computing. Remember that we have been trying to reduce the size of the computers, to be more specific of the chips, right? But there is a point where, with the current technology, where you cannot go smaller because they, like it's like you cannot cluster like so many of these chips because at some point they're gonna overheat and it's gonna be a problem, especially in everyday users. If you have a data center, that's fine. You can create a cooling system, but for the regular user, it's difficult to have something like that. So the quantum computing, it's kind of like opening a new door to increase the processing capacity. Most likely, we will see something like that in the next 5, I don't know, 10 years. I highly encourage you to read a little bit more about the quantum computing side. Okay, so let me show you the data sets for the large language models. So this is for ChatGPT, Cloud, Gemini, DeepSeek. So typically they use like something between 30 up to 60 terabytes. Of course, this is increasing. If you check the versions, the different versions, right now we're talking about ChatGPT 5. So most likely use a bigger data set. This is just for text. But of course, they require bigger data sets for video and images. And the tokens refer to the number of words or some in some cases like parts of the word. So they require trillions of these tokens to be able to train the models because they have billions of parameters. And that's relevant here because if your model has a lot of parameters, you will require a lot of data too. Okay, so maybe the sad news here is there is no universal cutoff for the or a threshold to start talking about big data. But I can tell you that it depends on the capacity, the velocity, and complexity. So it's not just the size, which can be gigabytes, terabytes, petabytes, exabytes, or more, but also the velocity or the speed of the transaction is relevant. So events per second. In some industries, this is really important, it's critical. We will see that in the next slide, that for some financial institutions, the speed, it's really important. And that's where they have problems when in some specific days, the number of transactions is higher that affects their infrastructure. Also, the variety, of course, if you are dealing not just with structured data, but also with unstructured data, that brings more complexity to your system. So the threshold will vary. It's going to depend the industry. It's going to depend on the time where you are located, and also it's going to, in some cases, it's going to be the volume, but in others it will be the velocity. In others it will be the complexity. Okay, so how can we experience like that we need to deal the data as big data? Well, you will find the threshold empirically when your analysis or when your infrastructure is going to start like to slow down. It's going to break down. So for example, Excel after 100 megabytes is going to slow down a little bit more. But now if you have, like a file with the size of 1 gigabyte, so most likely it won't be able to handle that file. So same thing with the SQL, if you have single server or even your libraries, pandas, if they are not designed to handle big data, then you will experience some delays or it will break down. So that's how you empirically discover the threshold. So at that point is where you need to, okay, so what can we do? Then we have some frameworks to know how to split the data in order to be able to storage the data, but also when you want to process that data. So the key ideas here, we will see them when we discuss Hadoop, Spark, and of course there are some cloud services that will allow you to handle these scenarios when you have reached or you have passed that threshold of big data. So as I mentioned before, different industries will cross the threshold in different ways. So for example, for Visa, the big company, they have a capacity to handle up to 65,000 transactions per second. So if there is a special day with more than that, then you might experience some delays or some problems. I have seen it in some companies. In my country, there is And there is something similar to what in the US you have the Zelle, for the transactions with the online, with your number, with your cell phone. So yeah, in different countries, I guess you have different companies like that, similar, which are more informal, faster, especially for small transactions, right? Well, during specific days like Christmas, or also at the end of the month, when most of the employees are getting paid, so there's a huge volume of transactions. Then typically, especially what I have seen here in my country is like during that days, people will start complaining, like because there are delays, or the platform is not available, it's not working. So that's because they had at that specific time they surpass the threshold, right, of their capacity. So it's big data for them, right, at that point. In healthcare, it's in some areas, genomics, for example, you have, like for a single patient, a lot of information. The other day I was talking with a friend. He's a researcher, and his main area is Alzheimer disease. So for a single patient, for a single individual, they have like 1 terabyte of information. So when he's running an experiment, like with 200 or 500 patients, for them, for the team, it's a challenge, like how to start processing all that information. In transportation, Uber, all these platforms, they have millions of rides per day. So they have a lot of information about the ride, the route, all the geographical information that they need to store. That's big data for sure. Walmart, so they have databases, that reach petabytes or more. And if we talk about social media, these companies are on the edge of big data because they experience high volume, the velocity is also high, and the variety too. So it's mentioned that Facebook typically they get around 4 petabytes every single day. So think about YouTube. Like when I think about YouTube, I'm recording this video, I'm using YouTube. So it's, like 30 minutes video, 1 hour video, and different users uploading all this information. That's a lot. Okay, so the first key point here is that big data is relative to your company. So yeah, we cannot just mention, big companies like Google, Facebook, because they know how to, like they develop most of the frameworks that we're going to discuss actually, and they know how to handle this. They have the infrastructure, but you need to be prepared as a small or medium-sized company. So how to handle, big data. So for a small business, like when you have like hundreds of gigabytes, I'm talking about Excel, it might crash for sure. For a medium organization on cloud, so you might have like, few terabytes. After that, maybe you're talking about big data nowadays. And large companies or tech giant, they will have, petabytes for sure or more than that. And in some special sectors, the threshold is not just about storage, it's also about complexity and the velocity. Okay, so now I want to discuss how much data do we really need. Especially, I'm talking about from the machine learning perspective, like what is the amount of data that you're going to use, let's say, to train a model. So let me give you a more general example. So imagine that you are going grocery shopping, you're going to the supermarket. So even if you have, like a lot of cash, a lot of money, it won't be smart to buy like 3 carts, right? A lot of food. Why? Because it will bring you some challenges. You have, let's say, like 4 carts, shopping carts full of, food. Then the first challenge that you have is, okay, how I'm gonna take this home, right? That will be the first one. Then if you make it home, then how you're gonna store all that food, because I guess you have a medium or even a big fridge, but if you have like a larger amount of the typical groceries that you buy, then that's going to be a problem, right? You're going to face some challenges. So it's not just about the storage. Then there is another challenge. So how you're going to process that? Let's say that you like to plan to do the meal preps. So if you have, like a huge amount of food, then that will take you a lot of time to clean, all that food and to make all the preparations. So it's not just about the problem. It's not just about the volume. It's also about the diversity and the quality. So for example, here, you will try to prioritize some type of food. I guess you would like to prioritize proteins, and you want to have variety because let's say that you're feeding, like a family of 4 or 5, then you need variety, right, to ensure that everyone will meet the requirements. So it's similar thing with big data. It's we need to know how much data do we really need. It's not about just taking everything that is available. We need to know, okay, this is enough. You need to identify. You need to know how to identify when you have enough data. But it's not just about the volume of data. It's also about the quality and the diversity. Is this a data really representative of the population or the system that you're trying to analyze? So my first lesson here is that more data isn't always better. It depends of the case. So we need to prioritize collecting better data first, and then once for sure you know that you have good quality data and that's the right path, then you can scale the volume because you can clearly justify the value of the data. So it's not just about just because typically what you will see is that people will try to collect as many data as possible, but again that's not always the most efficient path. So the amount of data that you require will depend of many things. So it depends of the type of problem that you're solving. If it's a supervised learning problem or unsupervised, then it will change the requirements. Same thing as depending on the type of data that you are facing, if it's just numerical categorical or if it's text or images, of course that will affect the amount of data that you need. So let me talk about a little bit of the Goldilocks zone. This is a concept inspired on the kids' storybook, like the Goldilocks and the three bears. So it means that not too little, not too much. So we need to find just the right amount. So because if we have too little data, that will affect the performance of your model for sure. So you won't be able to generalize. So that's what we call underfitting if we have too little data. Now, if you have too much data, so that's going to cost because you need to store the data, you need to collect the data, and especially once the model is in production, you need to keep feeding that model. So in some cases, too much data can be inefficient and it won't add value at some point. Okay, so for supervised learning, we can identify if our data is enough or not easily. I will show you with the learning curves that it's possible to see at which point our model is having a good performance and like more data won't add value. That's possible. So the sufficiency will be linked to the performance of our models. For unsupervised, let's say clustering, so to identify whether our data is sufficient or not, we can identify when our clusters are stable. Stable means like at which point, if you add more data, the number of clusters and the profiles of the cluster, they won't change because we are already capturing, like the meaningful information. So there are ways to determine this in order to avoid spending more money collecting more data. Okay, so sufficiency of your data is not just about quantity. Here, it also matters the quality and the variety. So let me give you more specifics. So in the example that we're going to discuss now, enough data can mean different things. In some cases, it's enough total volume. In others, it's going to be the variety. So let me show you. In the first example, text classification improves as the data sets grow from thousands to tens of thousands of samples. So that means that in that specific case, the volume is relevant. So if you increase the volume, so your model is gonna learn in a better way. Now, in some classification problems, such as the fraud detection, you have to look at not just the total data that you have, the complete volume. You need to check the total volume per class. So let's say you're analyzing whether a transaction is fraud or not. Let's say that's a binary problem. So this is a typical problem where you will have an unbalanced data set. That means that there is one class that will show more than 99% of the times in your data set, but there is a minority class, which is the fraud. So most of your transactions are going to be normal transactions, okay, and only a very small percentage of transactions they are going to be fraud. So here, when you need to know, what you need to increase is not just the complete data set. You need to increase is the minority class, the one that is very small, because you want your model to really learn to differentiate both classes. So again, here, enough is not enough in the total, it's enough per class. So that's important. Customer segmentation requires enough data to reveal stable clusters. So you need, like a representative sample of customers, and also you need to see, throughout time to see if they change behaviors. So it's important to analyze the stability of the clusters. For predictive maintenance, it's a similar problem with the fraud detection. You need to ensure that in your data, you really have a failures, actual failure, because most of the time, for sure, the data will show you a normal performing machine, right, or line. So you need to ensure that in your data, you also have examples of failures. So the model will be able to understand and identify that. So this is related to enough variety, enough per class. So here are some, let's say, guidelines, heuristics, or frameworks, if you want to call them like that, to ensure that you have sufficient data. So the first one, it's empirical. It's not a scientific rule, but it says that typically, this is especially for simple models, let's say a linear regression model. So it mentioned that for each variable in your model, you require 10 samples for each. Let's say you have 5 variables, then you will need at least 50 observations to train your model. So this is again a simple heuristics. It's not like a scientific rule. There is no formula for this. It's like a small guideline. Now it makes sense. If you notice, the key idea here is that the number of observations that you analyze, they are related to the number of parameters in your model. So that part, I think you can generalize that idea. If your model has a lot of parameters, then you need to have like at least more observations than parameters in your model. Okay, classification models will often need hundreds or thousands of samples per class. Again, not just the volume, but per class. That's really important. There are some techniques, of course. If you are, if you are not satisfying these conditions, there is some data augmentation techniques, right? Where you can, in a synthetic way, you can generate new data to be able to balance your data set. Or you can, of course, collect more data. It will cost more, but it's also an option that you have. Okay, complex models. Think about neural networks when you're doing some deep learning. They require more samples, more observations. Again, that's very similar to the first one, because if it has, like a high number of parameters, then more data is needed to be able to feed the model. One strategy, which we will see in the next slide, is learning curves. So they will show us if adding more data is going to improve our performance or not. Actually, our homework of this week is going to be about learning curves, because they help us to identify if our data is enough. Finally, in the bias-variance trade-off, more data helps with high variance, but not with high. It helps with the variance, but not with the bias. So let me be more specific about this. If you have a model, you train your model, and the performance of the model in the training set is good, but it's bad in the test set, then that's you're overfitting, right? So that's a variance problem. So if you increase your data, it might help. Maybe the performance is going to improve a little bit if you do that. Now, if you have the bias problem, then even if you increase your data, the model won't have a good performance. So let me give you a more specific example in that case. Let's say you have a linear regression model to predict a variable that is non-linear. So that's the bias problem. That's the bias problem. So even if you increase the number of observations, but you are still using the same linear regression model, then you won't fix the problem. You won't fix the problem. So that's really important to have that difference clear. All right, so let's see the learning curve. I really like this concept. It's very practical, it's simple and very practical. So the key idea here is the following. We want to find if additional data is required or not. We want to see if we increase, like the amount of data that's going to add value to our model, to our predictions. So let's say that you have 100% of your data. This is not your data, I'm sorry, this is the training data. So what you need to imagine here is that at this point, you already split your data. So again, this is all your data. So you can split 30, like 70% for training and 30% for testing, 80-20, even 90-10. Okay, that's fine. So the splitting was done before these examples. This is just the training data, just this portion here, just the training data. Okay, so with the training data, what we're going to do here is, okay, we're going to take only 10% of the data first, train our model. Imagine this is a classification problem. So we train the model only with the 10% of the data in the training set, and we check the performance in the validation set. So here, this is the point that we get. That's the point that we're getting. Now, we increase, okay, now instead of using 10%, let's use 20%. Now we use 20% of the training data and we train a new model with that information and we measure the performance. And that's the second point that you get. So you keep doing the same thing. You keep doing the same thing. So if you notice here, the slope, it shows that the model is increasing the performance as you increase the training size. So what is the meaning of that? What it says is that it makes sense to add more information. The volume here, it's relevant. So this model can use more data. That's what you are getting, because as you increase the training size, right, the accuracy, the performance, it's getting better. So there is value. Now let's see a second example. Now, if for the same data set, imagine that we experience this. So we start, we use 10%, this is the performance, 20%, 30%, but then at some point, you see that the model stops increasing the performance. So what you see here is like, at this point here, there is like a horizontal line here, right? There is no slope. There is no slope. It means that even if you keep adding more data, it's not going to add value. So if you want to improve accuracy, the model accuracy, you don't need more data. Maybe you need better quality data. Maybe you need to add more filters, different filters. You need to change the algorithm that you're using, but more data won't fix it, right? So this is one way to identify if the data that you have is enough, if you need more, or if you need less, right? So learning curves are really helpful for that. I will provide one example of learning curves in our Brightspace, or at the bottom of this video. I will provide the link with an example how to perform this, and the homework is going to be related to learning curves. Okay, so our conclusions is that missing key features, for example, cannot be fixed by adding more samples. So it's not just let's increase data that won't fix all your problems. It depends. It depends. Remember, it will fix when you have high variance, but it won't fix the bias problem. So when you have a class imbalance in a classification problem, so remember that in general you will require enough sample, not for the complete dataset, but for each class, right? So the focus is not in the complete volume, the focus should be in each class. Redundant data can increase costs without improving accuracy. So redundancy, when you have large data, it's possible that you have redundant data that is not going to add value. It's like, imagine that I'm teaching you a key concept in data science. Let's say regression model, a linear regression model, how to train a linear regression model. And then I show you 100 examples. Imagine the amount of time that I need to show you 100 examples. Like I will fit, 3 examples per video. So that's a lot, right? But at some point, like, after 2 videos, once you have seen, 5 or let's say 10 examples, that's more than enough. You already know the basics. You have covered what to do in each case. So if I keep teaching you the same thing, even if I change the examples, it's just redundant. It won't add value, right, to your learning. Same thing with the models. At some point, when they start seeing the same, similar examples, then the model is not increasing, like it's not improving the accuracy. Okay, so at the end, the key idea here is that big data depends of the companies that where you're working. It depends of your resources, right? It depends of the time that you're living, right? It will change. There is no specific threshold, and you need to be very careful with the resources that you have available. And one part of that is to know about data sufficiency. So it means that what is the right amount of data that I need, what is the right quality, and also the right diversity in my data. So with these key concepts, we can optimize the usage of our resources before we move, to big data. And that's going to be the focus of the first part of the course. So how can we do data analysis, machine learning with, with our resources by being more efficient? And then, of course, at some point and in some specific cases, we won't be able to handle, the amount of data and with the traditional tools. Then we will transition to big data frameworks at that point. All right. So I'm going to stop the recording for now. I'll see you in our next lecture.